for me drifting in here. My name is Jeff Harrison. I'm from Maine, and my background is consulting engineering as a forensic engineer. So I've been doing geothermal for some time, where I came at it from the aspect of looking at what everybody else was doing out there in the world of geo and re-engineering what they've done to improve the systems to make them more efficient. I saw a lot of systems that were using too much power because of their pumps, too much power because of not enough borehole, or a lot of water quality issues with open loop systems, a lot of failures, and a whole variety of things. And one of the things I quickly realized when looking at geo boreholes is that the borehole technology of 1.25" U-tubes, which originated out in the Midwest some time back, is really kind of geologically dependent on what might work best in different geological areas. Up here in New England, we have a lot different rock and ground geology than you do in a lot of other areas, where the rock has a lot more heat capacity to move heat through your heat exchanger or away from your heat exchanger, because we don't have nearly as much overburden in most locations. So what makes sense here isn't necessarily what makes sense in other places. So with that in mind, I've gone through and developed a way to make buildings near net zero energy just by designing the HVAC system a lot more efficiently, using a lot of small things all added together. When a typical building uses energy, it might be 60% heating and cooling energy and 40% plug load and lights and things, or a 30-70 split with the 70% being building conditioning, maybe on some more modern buildings that are a lot more tighter and a lot more energy efficient. But the big bulk of the energy used is, the HVAC. So if we can hit that HVAC number really hard, we can make it so that there's enough roof area to add PV to the building to get to net zero energy relatively easily. It's not really that hard to do. So if we look at a scale that has 100% of the median energy that a building might use, just by attacking the HVAC system aggressively, we can get down to the 25 to 30% value just to start with, then letting PV panels finish off getting us all the way down to net zero energy. We look at different system efficiencies, and these are color coded, where I got the propanes in the purple, reds are the oils. Different kinds of geo systems or heat pump systems are in the green, and you see they cover a big wide range, which is kind of distinctive for one reason here. Then they got the natural gases in the orange. Geo-Exchange can be done so that you've got the same BTUs per dollar system efficiency, this big bubble, sort of like a bell curve, where you got this 40, 50,000 BTUs per dollar. Geo-Exchange can be way up in this same number depending on how it's put in, or we can go to this extreme where we're now pushing the envelope of about 200,000 BTUs per dollar. Air source heat pumps are in here in that same range, the 50,000 BTUs per dollar. So there's a lot of variation in what can be installed. That same graph simplified down to just a couple of the basics here is that if we're looking at a hybrid thermal solar active energy recovery Geo-Exchange system, and we can get the highest BTUs per dollar and lowest CO2 combined into one system, where the only thing that can beat it on BTUs per dollar is a full-scale biomass chip boiler, which of course has high CO2. So it's sort of a win-win whether you're looking at trying to achieve low CO2 or high BTUs per dollar. One method that a lot of proponents of net zero energy like to use is minimization. They do a very bare structure, try to take everything out of the building that uses electricity. They advocate clotheslines instead of clothes dryers. They do all this other stuff to get to net zero. But what I say is we can build anything we want and make it net zero just by attacking the HVAC very aggressively. This is a building here that's on a New Hampshire lake. It's got a 4-ton Geo system, 13.4 kilowatts of PV, and it uses -2 kBTU a square foot a year in its first year. Last year, I think it hit -4. And that's compared to the average home using 60 kBTU a square foot. Now, he did go a little bit overboard for a residence on his PV system. You can see he put on his garage. But then this is a guy with a house with 2 refrigerators, dual dishwashers, a wine refrigerator, more routers and cameras and around the place than you can shake a stick at. His plug load is through the roof, and yet he's still a net zero house because his HVAC system uses so little energy. Here's another house right on the coast of Maine where it gets all the buffeting from the weather. 5-ton Geo system, 8.4 kilowatts of PV, and he comes in at a small, meager 8 kBTU a square foot a year compared to the average of 60. A building like this doesn't even pass the energy code when you look at how many square feet of window it has and what its load is for the BTUs per square foot for how much energy the house should be using because it's got so much glass. But he's still a near net zero energy home. So there's no compromises on what he wanted to build versus trying to get down to near net zero energy. Yeah. I integrated in a hybrid approach to the Geo-Exchange where I'm using the Geo-Exchange beds as a thermal battery. And I got some more photos of it coming up here. I'll show you. Pardon? Yes, I'm running the low temperature solar into the solar panels in wintertime. We're running 40-degree water up into those solar panels, getting heat all the time, quite productively. So it helps get a lot more useful solar into the system rather than trying to make hot water. So what I advocate doing is using this guideline, which is really following the basic energy code. It's not going to the super insulated or over the board insulation numbers. It's just building a good tight shell. Biggest variable is infiltration and doing something where you're going to specify that the building be blower door tested to verify that the contractor built building that's going to be tight is the biggest insurance towards making sure that the building doesn't have an excessive heat load. I find a lot of buildings with loads like recessed light fixtures with wiring chases that end up out in eave overhangs with fancy little roof thingies that end up leaking air a lot, and it can really sometimes double what the house heat load should be when you get to a lot of fancy architecture. So specifying air sealed construction to 1 to 3 air changes an hour at the ACH 50 numbers is really essential, and then just following the energy code to keep the energy use reasonable. And then spending the rest of the money on your Geo-Exchange system and thermal solar. So a compressor, I guess you all know, it's just a machine that moves heat from one place to another. And in the heat pump cycle, it can reverse, which direction it's going into. The key, and Ed touched on this quite a bit, is keeping the work the compressor has to do down. In older systems, the designs were always to use about 25-degree water leaving your compressor with 120-degree load water. And that work, just like going up a flight of stairs, is the work that the compressor has to do to lift that energy from 25 degrees up to 120. So getting that lift down is essential in reducing the amount of work the compressor has to do. So we've raised temperature of our loops so that similar to Ed's numbers, I'm using about 38 degrees for my minimum temperature going to the ground. And I try to keep my load temperatures between 80 and 95 degrees, somewhere in that range. So I'm limiting the amount of work that compressor has to do. Here's a graph from a job that we've installed where I'm measuring the temperature that the compressor is running at. Over here, it's either running at from the mid-80s up to about 115, 117 degrees. And then over on the right, the corresponding COPs that those temperatures are at. So if I have a radiant system that, and with this system that was being monitored here has a domestic hot water priority on it, where most of the heat is usually being used for radiant floors, and sometimes it goes to domestic priority to make domestic hot water as a preheater. But the COP varies between the 3.8 and about 4.5. So that change in temperature that we're pushing to make the extra domestic hot water can be as much as 20% more compressor power. There's a lot of systems I see installed where their radiant systems are designed to make the hot water have to be driven up to a higher temperature, so that they might be running, 105 up to 125 or 130 to get the job done. So designing your terminal infrastructure so that you can use lower temperatures has a big impact on how much energy you're going to use. So designing things with lower temperatures is critical. On the air side, a lot of the systems I'm using a 95-degree water. So if I have entering fluid temperature of 95 degrees and using somewhere between a 10 to 15 degree delta T depending on the coil selection, and this is just a cut sheet from one of the manufacturers I got on one of the jobs we were doing. We're getting approach temperatures of leaving dry bulb of about 1 degree, or here it's 3 degrees. So we're getting good leaving air temperatures with low temperature water, which goes back to how much energy is that compressor using to give me geothermal energy inside the building. It's not hard to keep your temperatures low, make the job work. The other thing is we're using is a thermal care turbo core chiller made by Danfoss, which is a magnetic bearing chiller. In here inside the compressor is a shaft and a 4-inch impeller that spins around 30,000 RPM. The efficiency of this machine is about double or a little more of what the box compressors with their scroll compressors can achieve. So right off the top, we're getting COPs of the machine of between 8 and 14 with EERs of 27 to 47. So on a commercial scale job, this kind of equipment can start on a system with 45 tons. Yeah, so 45 tons and up is where we start looking at this kind of equipment. This magnetic bearing that's inside the compressor also improves its maintenance cost. Because there's no friction, the parts don't really wear out. These magnetic bearings float that shaft up, and as it's spinning at 30,000 RPM, if it loses power, it's also a generator, and it makes its own power until it safely coasts down to a slow enough speed to rest on its seat. So it gives you a lot higher efficiency with one other aspect. All these other machines, if you look at their kilowatts per ton produced, centrifugals, screws, and scrolls, they all produce their efficiency at its peak, usually around 60 or 70% part load, whereas the magnetic bearing chiller, being a different dynamic, it achieves its peak efficiency between 30% and 40%. So the times when we have the highest number of bin hours at our usual light loads, we also have the highest efficiency of the machine. So that's another way that it ends up being more useful on an annual basis, because we're operating more hours at peak efficiency. When it comes to the ground and what we put in the ground to get our heat out, the equation Q equals UA delta T is the same equation we use for all our heat transfer equations, and it really governs everything going on down on the ground. The basic design of the 1¼ U tube has a very small area of plastic pipe in contact with the ground, and if we want to make the system more efficient, we've got to sacrifice a little bit on the delta T. And then there's the U, which is the coefficient of heat transfer that the material has. So what else can we do besides a standard U tube that's kind of become the industry standard based on where it originated out west? Here in New England, it's going to be a lot better for this territory. I know you probably saw this out. Ground affecting that part of the equation. We can also affect delta T by dumping in thermal solar. And that goes to the question about, what am I doing with the thermal solar? I'm taking and tying in the Geo water on the source side right at 40 degrees and running that into these thermal solar panels to, just get a 4 or 5 degree temperature rise, which you can do in the wintertime, even on a cloudy day. You'll get a rise of several degrees on thermal solar panels. You can't make hot water with them, but you can certainly make cold water just a touch warmer. And for the delta T's we're looking at from a regular ground heat exchanger, those couple of degrees can be quite valuable. And that all goes to, sizing the equipment, how much borehole we need to attach to the heat exchanger to make the system work. Another option shown on the far end there, so in other states besides New York, that's something to use. But in New York, the twister has a huge advantage in what can be done, making the standard U-tube an obsolete design. Yes. I usually use drain back systems, and glycol is optional. You don't need it, but it's a good thing to put in sometimes for safety in case something breaks. Get water trapped up there, or the pump comes on inadvertently at the wrong time. So it doesn't hurt to put glycol in. You're not going to be running at cold enough temperatures. You're going to be paying a big penalty for putting glycol in. But I always use flat plate panels, not evacuated tubes, because at low temperatures, flat plates are more efficient than evacuated tubes. We're not trying to get hot water. So the right kind of panel for the right application, and Geo hybrid cold panels is a flat plate. The other thing we're doing is Geo Performance piping. Now this piece of pipe here that has the effect of reducing its R value by more than half. So it has a much greater ability to put and take heat into and out of that borehole. Now, if I had a job that was like a swimming pool, where I was going to heat that 24/7, 365, that pipe makes no difference whatsoever, because the limiting factor is not the pipe, it's the ground around it and its ability to bring heat back to my borehole. But if I got an average commercial building, which is going to cool by day and heat by night, like Ed pointed out, more and more buildings are becoming cooling dominant, and more buildings on a commercial type are cool by day, heat by night buildings. And with that type of load, the put and take, the ability of this pipe to have a low R value right at the pipe wall, so it can put that heat into the ground more efficiently in the daytime, take it out more efficiently every night, back and forth, is where that pipe has a huge advantage in reducing the overall borehole field required. Here's a graph from an under slab thing I do. This 3/4 inch pipe that's shown here is installed under the slab of an existing building. Since I'm using 38-degree water, I don't have to worry about frost heaving the floor or causing any damage. I'm using straight water, no ethanol, no methanol, no glycol. And this is how the system ran, measuring the bed temperature, where here at the beginning of the season, we started up, it was running, 45, 50 degrees. We're adding thermal solar to it throughout the day. It's going back and forth, and this is that same GeoPerformX pipe where as we're adding heat to the ground, that pipe is helping us put more heat into the ground more efficiently, and then taking it back out at night, helping to keep the average temperature hotter. At the end of the heating season, we were up to about 55, and then this particular building had the bed horizontally divided into two sections. There was the underslab section, which had the thermal solar panels tied onto it, and then there was a small section outside in the area, like under the under drain, that was used as the cooling. It only had a 2-ton air conditioner for summertime cooling, so we didn't need as much heat rejection. So we're storing the heat from the solar under the building in the summertime, and in the wintertime, and also in the summertime, we're heating up the outer bed with the air conditioning. So here, when the system started up in the fall, we're having a COP of around 5 for the system, and we peaked out at a low of around the mid-4s for a COP. Now, most horizontal systems that are out there, and you look at, they're going to be averaging around 2.8 to 3. They're not even on the chart here, because of the temperatures that they normally operate at. Most horizontal systems, run usually at best around 38, and then go down to the 26 degrees, that sort of range. Also, in looking at, yep. Yeah, when I first started doing this, I was using slinkies. And I quickly decided that doing slinkies was a bad idea because of all the number of pipes you had to bring up into the foundation, manifold together indoors. The labor was intensive with too many slinky runs. So then we started switching to doing a pre-manufactured pipe where yeah, whatever the civil guys are doing to get rid of water, I'm 6 inches lower than whatever they did. So I work with them to whatever detail they want to do to get rid of the water from the building, and I just go down 6 inches more and put my bed in. For vertical designs, the other advantage you get from the deeper designs is it gets about 1 degree warmer every 100 feet you go down. And I also find from my measurements that the deeper designs have a faster recovery rate. Because of the higher delta T's down there, they're able to drive the energy back to the place where you took the energy out of more rapidly. So I'm getting a better quality of temperature, getting a temperature that recovers faster, and I'm putting in that concentric with a lot of area that's going to give me very high surface area to bring heat into my system with. When it comes to the different designs and Q, the amount of heat you can get into these heat exchangers, the old design is significantly lower than what we can do with these more modern designs, the twister or the concentric, as far as the BTUs you can harvest. And you're still limited to what the ground can produce for energy. But there is a variable where each heat exchanger has a limit on how much heat it can obtain. This one. If I look at the equilibrium point, what can each borehole produce at that? If I was going to do something like I mentioned before, if I was going to heat a swimming pool, how much borehole do I need if I'm going to be taking heat out of the ground continually? For the standard U-tube, it's about 220 feet per ton using 32 degree water. That's 4-inch concentric design That equilibrium point's about 135 feet per ton. So there's a definite difference between the feet per ton required depending on what you're putting in the ground. The twister down here at 160 feet per ton, again, is a big improvement over the 220 feet per ton. Now, if you're doing a design, you don't put in this many feet per ton normally. In this area, you're usually doing something between 150 and 180 feet per ton. So for this 4-inch design, it might be between 95 and 120 feet per ton. And for the twister, probably the same, something, well, maybe 100 feet to 130 feet per ton, depending on what your load diversity factors are. At 38-degree water, those same values, and again, because I'm using warmer water temperatures, I look at the same curves of what happens with the warmer water temperatures. With a standard U-tube, I'm up to 279 feet per ton, which would definitely be cost prohibitive to install something like that. But because I'm using an advanced heat exchanger, I can put in, maybe I'm not going to put in the 165 feet per ton, but maybe I'm putting in 140 or 130 or 120. I'm picking some balance between giving myself more heat exchanger to run warmer and reducing the feet per ton to reduce the installed cost and trying to meet somewhere in the middle. I'm not going all one way or the other. Although you could drive this to the extreme of, you could install this 4-inch concentric down to 95 feet per ton, put the methanol in it and really, drive the dickens out of it for a really low-cost system. But that's not the point of a net zero energy building. The net zero energy building, you want to find some happy medium to arrive at. Here's a little bit more detail on how that concentric works. It's all built of fittings and pipe. There's no special parts made for this at all. Everything is off the shelf. This is just a standard tee you can buy with a couple of reducers. Water comes in the side, goes down the annular space between the pipes, gets to where the cap is on the bottom. Cut the bottom. The bottom 60 inches. And then the water comes back out the top. This top fitting here is an electrofusion fitting that makes the final joint between the 2-inch pipe that came up through and the 4-inch reducer. So again, everything's off-the-shelf parts, nothing special, nothing fancy, no patents. Yeah, and it produces about the same, energy as a standing column will without the bleed. There's a picture of it being installed. They've got the pipe held in an upsy-daisy and using a regular manual welding machine to weld the joints vertically. There's a picture of the crane holding up a 50-foot stick. It takes a crew 15 minutes to go joint to joint building these. So it's a one-day job getting an 1,100-foot borehole down. It's in the realm of most drillers except there's a group of guys who just do small residential wells. It's beyond what they can do. But any of the big guys around, they've all got rigs that can easily do that. Now, it still depends on what you're doing in different areas. You've always got to match what you put into the ground to the local geology. I'm not opposed to doing anything as long as it matches the local geology, whether it's putting a tap into an aquifer, taking the water out and putting it back in the aquifer. If the water quantity is there and the water quality is good enough that you're not going to have any problems, fine. Whatever works as long as it works with the local geology. I do a lot of open systems myself when I get down to Cape Cod, where it's all a natural sand aquifer and all naturally filtered water, very clean, easy to deal with. You can do some other things like, a fellow in the audience, Sam, is tapped into the Syracuse salt brine aquifer, which is as gnarly a water as you're ever going to get. He just runs it through a titanium heat exchanger. But because he's in an area where there's all this water just sitting there, it's easy to just move it up through the heat exchanger and back down it again and keep the cycle going. So if your geology, works for that, fine. When I'm doing these 1,100 footers, what works best is someplace with good hard granite and nice dry holes. You start running into excess of water and the drilling depth gets hard, this is not the thing to be using. If I've got a cooling dominant building, I can get rid of more cooling in a twister I can get rid of in the concentric, because concentric goes down where it's warmer and I'm better for heating. If I got a heating dominant building and I'm not in New York, I'll lean towards the concentric. If I got a cooling dominant building, I'm leaning towards the twister. Twister is more cost effective to install down to 500 feet than it is to install the concentric. Dollars to install each type of system. So, there's no one way to do it. They all work. It's just what's going to work best for any particular customer. I like to stress risk. Closed systems always pose less risk than open systems, because anytime you're dealing with something open, another variable of what could happen to that resource, contamination, something getting into the ground you didn't mean to, or something coming into your system and fouling it. Closed systems definitely have less risk than open, but if you assess the risks and weigh the advantages and pros and cons, nothing is really off the table. I will say that the most systems I've had the problems with are standing columns that use the same water over and over. So if I have to go open, I like the pump and the dump where you're pumping out of one and into two others as a diffusion, as opposed to the standing column. The standing column is the one thing I really kind of shy away from. Not that there aren't some good ones out there. It's just that, what's the risk value and what else could I do? So I'm doing a lot now, more than I used to think possible with horizontal, and I was really impressed with how much Ed has done horizontally. I'm finding mixed results. Sometimes I get ground temperatures that are astoundingly colder than anticipated at startup, sometimes as much as 10 degrees because of local groundwater flow conditions, getting into the ground with surface water that might have been subcooled. I'm having a much better success when I go under the buildings because the buildings are sheltering the pipe more. Plus, when we do that thermal solar additive to the bed, there's some pictures of some going in, but the cost is so much cheaper if you can put these in. And I've done these where we've gone into a place like what we are seeing in this pit here. And then they'll put in a 1 foot layer of good structural fill, and then go in and put all the footings and build right on top of it. Right above the the nice grid pattern of pipes you put in. And here's the grid we talked about. You can see the header there at each end, and the 2x4s on the side there. As the guys backfill it, I get guys to sort of comb the pipes out. Those 2x4s have little notches cut in and the 9-inch spacing, and they sort of comb through as the guy is sprinkling dirt around, and you can get a nice spacing on the tubing. There's some of the spacers in action. Now this job is going in inside an ICF foundation on a it was 6,000 square foot building or so. It was pretty big, but it reduced. You can see the 2-inch pipe up here that goes off to the mechanical room. There was 3 zones inside this foundation, so there was 6 pipes going to the mechanical room, which if we tried to do it with slinkies would have been totally abominable. So this has been working really well. The efficiency of doing something like this and then tying it in with thermal solar as a bonus to store that heat in the same area with another layer of tubing above it. Usually I'm doing something much simpler for the tubing for the thermal adder pipe. Sometimes I'm just taking a 2-inch pipe and making a bit of a coil or a bit of a run through the area, not being too particular about how it is other than to just evenly cover the area. But it's nothing like the heat extraction pipe to get the heat in. Here's another horizontal grid going in. This one's going to end up 8 feet deep in a place that was mostly fill. They actually only had to dig between 2 and 3 feet deep to put it in because there was a hill here already that was going to be a parking lot. And I insisted they go down a little bit deeper for the final depth because if you're going to plow the snow off it, the frost goes down deeper, and we're trying to keep the temperature up. This one's being filled with stone dust, and that actually works quite well for the initial layer. What you really want to have in all these beds is water movement is key across this pipe to make sure it stays wet. You don't want to put this pipe into a clay material that's going to act as a dam and prevent water from coming from somewhere nearby and going across your pipe and bringing you fresh energy. You want some kind of sand or stone dust or something permeable to help some water exchange. Supposed to be a slide there, but it's like it's a DOA. The basic system that I'm doing for a hybrid is a simple diagram that works for everything from residential right up through commercial. It's basically a hot tank and a cold tank with a compressor in between. It just moves energy one way. And I say compressor because it's really the chiller on a commercial scale, which can only move one way. It's not a heat, but you could do this with a heat pump. But having a hot tank and a cold tank gives us the ability to do simultaneous heating and cooling as most commercial buildings need. We can take off the hot tank and provide heat to all of our heating needs, take off the cold tank and provide chilled water for data centers or whatever needs the cold water, and then bring extra energy in from recovery. I'm real big on recovering all the energy we can and recycling what we can in a building. If we have a school building with all the CFM of exhaust, that exhaust is 70 degrees. Even if we use a heat exchanger, if we have a dedicated outdoor air system, a DOAS, that exhaust is still going to be on average above 50 degrees. And we can recover energy into our cold tank, which is always going to be at 40 degrees, and get energy into the system that doesn't have to come from drilled boreholes or surface area of covered horizontal field. We could also tie the thermal solar in, where the thermal solar can be done two ways. And this is a true hybrid integration, which I got a patent on this for the way it's being performed, because nobody had really done this before, where the thermal solar comes into the hot tank on the shoulder seasons when there's plenty of thermal solar to make the water hot enough to heat the building. And then it switches over to doing a mixture of potable water heating during noontime when the sun's out, and going and using 40-degree water right to those thermal solar panels to run the rest of the time. So the solar panels don't sit around inactive. They're getting, did you have a question? No. The thermal solar panels don't sit around being inactive a lot. They run a lot of hours. So that all helps to downsize how much geothermal infrastructure you need, keeping the cost of the geo system down. This is an energy model I had to build in order to look at this whole hybrid integrated system because it's kind of unique. I look at the hot tank, the cold tank. I have a finite element analysis built of my own that's the ground source, different concentric rings of soil and the different temperatures it tracks. The chiller, I can have a boiler that's going to provide peak loading if I want to use it. I have my thermal solar tied in, and it can tie to the hot tank, or I can tie to the cold tank. Then I have active energy recovery or active energy heat rejection. Like a lot of things Ed was pointing out, I might want to cool this borehole down at night when I'm not using it. If I know that in the summertime my temperatures have been creeping, I can run this exhaust fan in the nighttime and just dump some heat. And then a regular 4-pipe air handler system using low temperature coils, the 95-degree water coils. You combine this into the model that runs the hourly calculation for a year to size up everything together and come up with what's going to work for a near net zero energy building. This is that same diagram converted to an operating DDC control system in an operating building over in Springfield, New Hampshire, or Massachusetts. Got the hot tank, the cold tank. It's got the geo system tied in with it. It's got an active energy recovery unit where this chilled water can either be bringing energy in from the DOAS or it can be being used as chilled water. It's got a thermal solar system that's tied in where the solar comes in, can go to the hot tank or go to the cold tank. A lot of times the controls can run it so that the thermal solar is running. There's not a lot happening in the building, and the solar heat's actually just going out to the boreholes to be stored for later. And then it's got a peaking boiler. I find on a lot of commercial buildings, if you really got to get the installed cost down, and especially on a lot of retrofits, I usually do about a 60-40 split on the MBH load. So if I have 1,000 MBH, I might do 600 alternative energy and 400 peaking boiler, which usually adds up to about 15% peaking boiler gas use per year. So that 40% of the load you've shaved off your geo infrastructure is only 15% of your annual energy use. Seems to be about a pretty good mix for most buildings I've looked at. Bottom line, where did we get by doing all this integrated hybrid energy recycling, yada, 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 yada? 10%. Annual COP of 10 for this operating system. So for every 1 kilowatt we bought, we harvested 15% of it from thermal solar energy, 45% from the Geo-Exchange, and this particular model that this was based on had 6 of those concentric boreholes. And then 30% is from the active energy recovery ventilation system. So that can be a big factor. And it depends on the building. You know, office buildings with lower ventilation rates, you know, might use it less. Buildings with a lot more population density or a lot more theater type buildings might use a lot more. But a COP of 10, you know, that's near net zero energy target right there. Go ahead. That wasn't on this one. I've done a lot of these, so this is a picture of some of the another job with thermal solar panels. This one's actually down in Hyannis, down in the Cape. Again, all winter long we're pumping 40-degree water into these panels. In the summertime, they're producing hot water for space heating and domestic hot water. Here's an efficiency curve on solar collectors, and I mentioned using the right type of collector for the right type of application. You know, the evacuated tubes, you know, especially if you have roofs with limited area, all that space between the tubes is wasted solar energy you can't get per square foot, and also the efficiency of the collector itself at those lower temperatures peaks a little higher in the flat plates. So we use those. Active energy recovery. If I had an existing building with runaround glycol loops, which you still find in a lot of older buildings, where you have a coil in your exhaust and a coil in your makeup air, and you just have a glycol running between them, the area under this blue line, and this is the bin hours that it would occur and the different average temperatures, you know, sorted into bins for the year. This area under the blue line is what that runaround loop would have recovered. By using active energy recovery and using 40-degree water in that energy recovery coil, I can get all the area under the red line recycled into my building. Now this assumes I'm a building that can use that energy. Not all customers can. So again, you got to match the right thing you're doing to the right customer. If I have a hospital that's using reheats on their VAV boxes, that's a year-round use that can easily use all this low-grade energy. Any kind of processed food application that has a lot of wash water can usually use it. So any place that can use the energy, you know, it's worth putting in the oils that are going to harvest it with that 40-degree water back into your system. Some of the average cost per ton for installing different geosystems, the concentrics and the horizontal. I should have a twister on here. Twister tends to run a little bit less, probably more like $2,400 a ton, a little bit less than the concentric, which is why if I can't do a shallow, if I have to do a shallow design, I switch right to the twister because I can do it cheaper than I can the concentric. But you get a huge drop in cost when you switch to some of the horizontals. Now, I've done a lot of analysis of like a nursing home where I can cover all the area under the nursing home building, which is a footprint that's spread out pretty large, then maybe supplement it with 1 or 2 or no boreholes, depending on the job. And on new construction, can usually get paybacks now down to that 2 to 4 year payback range, because we're shaving off a lot of the infrastructure costs and getting the cost of operation much more efficient with that 200,000 BTUs per dollar. If I'm looking for the best, shortest ROI, first thing I eliminate is the thermal solar, because it has a good long-term ROI, but it's still more capital stuff you have to buy, and it will lengthen out the payback a bit. So it depends on your customer's goals. If they're looking for and have a little bit more tolerance for a little bit longer ROI, like 6 to 8 years, then you add the thermal solar in, and they're going to really benefit the out years because they've added all that free solar energy. But if they're really sensitive to a good ROI of 2 to 4 years, you've got to get rid of the thermal solar. Just go Geo. Inside the building and pumping costs. This is a huge thing. When it comes to how much energy is a building going to consume, a lot of times I've gone and measured and found that all the pumps in a building might add up to 30 to 40% of what the compressor is doing, which is outrageous. But I find it over and over again because people are using rules of thumb for engineering in load side based on boilers at 106-degree water. We're using 95 to 120-degree water, and these systems run a lot more hours per year than what boilers run. So it's much more important to size things up. So basically I say whatever size pipe you came up with before you used to do things for boilers, everything is one pipe size larger. That's all. One pipe size larger. VFDs and all the ECM pumps that are available now, I try to design all systems to stay within like the Velo pump range or a Grundfos Magna 3 to stay within the ranges of what those pumps can do. And then you're going to have a head loss that's going to be really low pumping cost. I had a different slide here. Basically, if you go to that rule of thumb of, if I came up with a pipe size that was going to give me the 4 to 5 feet of loss per head per 100, and I go up one pipe size, that's going to reduce your pump power by a cube factor or about 66%. Your horsepower just drops off. Just following that one rule of thumb, one pipe size larger. Hybrid application. When it comes to getting rid of heat in the ground, and Ed did this a lot in what he was talking about, but I really favor doing this because what we should be doing is something new and different. Just because we can get rid of heat in all of our heat in the ground doesn't mean we should. What we should do is to try to do something better than what we could do by getting rid of the heat to the air, which is to get rid of all the heat we can easily to the air at a lower cost, and then use the ground to get to a new level. How low can we get that condenser water down using the Geo? Instead of letting the condenser water drive up to 85 and 90, like most of Ed's graphs were showing, let's get our condenser water down to 85 like we used to, and then get it down to 65 to 75 with Geo as a next level of energy efficiency. Again, if we're trying to get down to net zero energy buildings, we got to think of something a little bit different. So just because we did Geo doesn't mean we want to get rid of all our heat in the Geo. We want to do something better. Peaking boilers, I just mentioned those quickly before. If you want to get rid of some of the capital costs, especially on retrofit jobs, doing that 60-40 split, using a condensing boiler of some type can be the best way to get that load down and cut down your borehole required. And this is the bin chart that shows that 60-40 split, where all the green dots in the area under them is the alternative energy, and with the small number of bin hours that you have at the higher load factors, this is that 15% of the annual energy with a 40% peaking boiler design. ECM pumps. Another thing to consider is some of the things in piping. Like you can see this installation here. This is a pipe that comes along to this pump that is a single pump in line. What's wrong with this picture? It's got the inlet conditions. What's this thing here? It's a big check valve. It's not even a dual pump system. What's this check valve doing? I don't know. It's sitting there eating up hay. But in this application, it serves no purpose. I find a lot of things, I find a lot of variable speed pumping systems still installed with triple duty valves. You know, they leave them wide open, but it's still a valve with a relatively high head loss when, you know, a nice ball valve would have been nice. And if you did a dual pump system, you know, a pair of nice duo checks or something that, you know, is going to have a low head loss rather than putting in a triple duty valve. I also find sometimes people doing variable speed pumping where they're still putting in a lot of three-way valves when all variable speed jobs should be two-way valves to actually reduce the flow of water, unless you need the three-way valve for some other reason. And then balancing valves. When it comes to the balancing valve, if you're doing variable speed pumping, you have to be putting on automatic compensating valves that can adapt themselves with their internal springs to balance the system under different pressure conditions as the flows change in the piping. And I still find jobs installed brand new with TACO manual balancing valves that can't be balanced in a variable speed system. But I see it over and over again. So the systems end up never being balanced and end up wasting a lot of pump power. Usually about 40%. Usually you've gone down so low that some jobs it may be as high as 60%. It kind of depends on where you were in the pump curve and when you're going to get some useful flow. Some pump curves you might be down to 60% and all of a sudden your flow just goes to almost nothing. You can also, in a pinch, and I don't do this unless I have to, is to put those kind of pumps in series to get a higher head pressure. You can also get the models that have the dual heads on them for higher flows. Here's a job I looked at. It was a residential job, but we measured up all the pumps with current sensors and measured 28% power draw on all the circulator pumps compared to the compressor power. So this was a homeowner who was very disappointed with his power bill when he got it for how his Geo system was operating. And, you know, it operates 3,600 hours a year, and all these 11 pumps just cranking away, burning amps. So we do a lot with, you know, zone valves and variable speed pumping. Piping, when it comes to doing the load side piping, as an equipment supplier, I'm trying to get people now to switch to using, since we're using low temperature water, using low temperature piping like regular HDPE inside the building. You know, we're only handling, you know, 95 to 105 degree water or 40 degree water. We can switch to a lower cost pipe which has all these different methods now to make the joints. We got down here we have this newer induction fusing, which is kind of like microwave, where you can dry fit the pipe together with these fittings. You've got regular butt fusion, you've got electrofusion, you've got socket fusion. You've got all these tools to make this system go in for a lower installed cost with a larger pipe diameter and lower head loss. So this is another small piece of how can we get to a net zero energy building cost effectively by thinking about new piping materials. HDPE, low cost, easy to install, and very long lasting. No corrosion, no corrosion like in a steel pipe system. Geo-Exchange. Just because we've done something with Geo-Exchange that's good, we don't omit doing our regular ERVs. ERVs, when they can be installed in new construction, are very cost effective and a good way to help get our load down, which again, Ed's point, get the load of the building down to make your Geo system more cost effective. So never eliminate the ERVs from the design. Controls. There's a lot of simpler ways to do controls than some of the elaborate DDC systems. When you get to these mid-sized commercial buildings, smaller office buildings, if you look at a DDC budget, there goes your whole HVAC budget right out the window. But there's a bunch of companies that make different kind of Wi-Fi thermostats that are smart, controlled by web, and a bunch of other similar companies that make web server type stuff that's can be configured at a much lower cost. With these Ecobee equipment, you can tie on auxiliary boards to those thermostats that give you the ability to monitor. Actually, you can monitor like up to 48 different points off of one stat, although it gets a little cumbersome. I usually don't try to do more than 8 per stat. But you can measure temperature and anything with a 0 to 10 volt signal, like a current sensor. And that all goes to a data server at Ecobee, and you download the data and look at it on graphs. And it wasn't a DDC system and didn't cost an arm and a leg. So there's a whole lot of in-between things you can do with products that are available, and they're changing every day out there. This stuff is really evolving quickly on what you can do now. There's a lot of neat systems coming out that integrate, everything in the house with your smartphones and your lights and your hi-fi system and the thermostat all into one thing. Some really cool stuff out there. It's not full-blown DDC. And just again, drive home the point of all this stuff I've just gone through. It can be done very cost effectively by taking out and getting rid of the boiler altogether. Just thinking, putting in the chiller, going as much horizontal as possible, getting the cost of the installation down by doing energy recovery and reducing the borehole infrastructure. I could look at a job like this, which was a nursing home in Vermont, and come up with about a 2-year payback on new construction going Geo with a near net zero energy design from day one. This job would have had an average COP of about 7 because they wanted the short ROI, so the solar was taken out right off the bat. So that goes from a COP of 7 or 10 down to 7, which is still not a bad place to be. So the key to a lot of this is that Danfoss compressor on the commercial jobs with its extra high efficiency. Here's a job we looked at. This is the Springfield one. It's got 6 boreholes installed in this urban environment where this is all the area they had, and they just barely made it with the 6. It would have taken 27 regular U-tubes, not even possible to consider Geo had the concentric not been available. Another job where we looked at active energy recovery only. This was not a Geo job, but we used the Danfoss compressor. Typical in a lot of old school buildings, there's no place to run ductwork, so you can see we ran all this ductwork outside in these attic spaces, put in all these new air handlers, and they're just a bunch of runaround loops with a Danfoss compressor tied onto them, recovering energy. So we went to this building, which originally had all of its unit ventilators boarded up because they're all broken because they all froze. Nobody's got fresh air. The CO2 is through the roof. Tell the building owner to come up to code. It's going to cost, so much extra energy per year, and everybody fell off their chair. Well, we went in and put in this Danfoss Turbo Core energy recycling active energy recovery system. They saved $62,000 a year over their existing fuel bill, on top of bringing in all that fresh air that was never being brought in before. There's another picture of another Danfoss compressor. Now, when it comes to looking at Danfoss compressors, a lot of chillers like this one you'll see here, this is on a Smart machine. Train also makes them, York makes them, and a bunch of others. I don't use these after having used one. A HVAC chiller, which has multiple compressors per chiller barrel, is not the thing to use because Geo systems need more flexibility and variability in how they can respond to load conditions. So the thermal care unit I showed you earlier in the system has 1 compressor per refrigeration circuit, so that a compressor can come online immediately and go offline, and it stages in modules of 60 to 90 tons. That's the kind of unit you got to get as opposed to an HVAC chiller. If you go to Crane or New York and tell them what you wanted, that you saw what I did here and you want to use one of their chillers, which has a Danfoss on it, they'll run right away from you. They don't even want to hear it. So there is a couple of other companies that put the Danfoss on a single refrigeration circuit machine, but one is Arctic Chill and the other is Multistack. But the Multistack people weren't so fond of this either. So Thermal care loves it though. So that's pretty much what I've got to say, and what I've been doing for the last 12 years is, how to make Geo meet in the middle somewhere of getting the operating cost lower and getting the installed cost lower, and bringing those two ends together through a whole variety of aspects of, improved materials, bigger pipe sizes, making sure the pumps are small, getting my water temperatures up on the source, getting my water temperature down on the load, keeping all that stuff in mind at the same time. How low of an energy building can we get? And we can get down to that COP of 10, which is huge. And it's not that hard, and it can be done with a good payback. For the building with the thermal solar, that same building that showed the two-year payback without the thermal solar could have been between 4 and 6 years by adding the thermal solar. So, any other questions? The 3/4 inch U-tubes, when you get the four teamed up, are not a pump penalty. When you start to hit about 450 feet, you start to hit a point on the curve when it's going to start showing up. You can push the U-tube of the twister down to 500 feet, but you're going to start impacting your hydraulic head. So you do hit kind of a limit in there. I like to keep the twisters down to 450 feet or so or less, because I'm starting to get into that point on the curve. When it comes to the concentric design, the 1100 foot actually has a very low hydraulic loss because of the surface area is so large inside there. I have done a lot of double U-tubes, but I've done 1.25 inch doubles, and usually that's about a 900 foot limit before you hit that point on your hydraulic head point where you start to pay a penalty. So that's my rule of thumb is 900 is W's are good with 1.25 inches to 900 feet. I haven't tried 1.5 inches just because I haven't, but everything works if you just watch your numbers. Anything else? What we do is we grout it from the bedrock up. We treat it like it was going to be a standing column well in design, where it's grouted from the bedrock up to prevent surface water from infiltrating into the deeper groundwater. So we're usually only grouting the top, 50 to 100 feet or so, or 150 feet. I do have a design we've used on an application where we had to grout from the bottom up. It tends to drive the cost up, and it's something that I would only use under a circumstance where we were going to this design for other reasons than cost and payback. Ideally, the concentric works best when we can design it and install it just like a standing column, grouted from bedrock to the surface. The twister, of course, is grouted from the bottom to the top through that pipe in the center. Pipe goes perforated, goes out. Definitely a big advantage over traditional 1.25 inch U-tubes, and again, in my book, it's an obsolete design that has passed its day. Water is key. The heat transfer rate of heat into those pipes in a horizontal bed changed by as much as 2 to 1 between bone dry and saturated. So I usually work with the site and whatever's going on to understand how wet my soil is going to be, and often incorporate maybe the rainwater pipes going to a gravel catch that comes down and fills my level of sand with fresh rainwater if it's going to be dried out. If I'm on a clay site and they're digging, I always make sure that they don't dig a trench from my bed area, that they were bringing an electrical conduit in and filling with nice sand all the way out to some lower point that's going to drain dry. I make them put in a clay dam in any trenches they build, that if I had a clay site that was going to retain water, that I'm still going to retain water. So you got to kind of work more with the civil guys and understand that, yes, I need water and I need to do something to make sure my pipe is wet. There's so many variables, it's really hard to go into. No, I cover all over from all of New England states and New York. Yeah, the only thing I would do would be to make sure I stay a little deeper in a parking lot because of the frost depth. The other thing I've done is, lost my train of thought. Sorry, gone. Anything else? All right, well, thank you very much.